But in these problems, not only do I want to know the accelerations, um, which I have, but I also want to know the tension. And that tension is between the two objects when it's moving. But we have to realize that, that tension, as A is moving forward, this rope is, A is trying to move forward, but that rope is connected to B. So, you may have experienced this. You're trying to move forward, but somebody's grabbing on from behind you. And so you're trying to move forward, but because they're connected to you, you can't move freely. Because as you try to move forward, that connective force is trying to hold you back. And so the inertia of B is preventing A from moving forward because of the connection. Now, the reverse or other way to look at it is that string is connected to B, and so when MA starts to move forward and get some tension in that string, it's that same tension that's going to try to pull MB forward. And because of this, we can hopefully easily see that this is a set of action-reaction forces. Right? We have the force of tension of A on B and the force of tension of B on A. They're equal but opposite. And so that force of tension can be found by either analyzing the motion of either object. But the key to that is that we have to analyze the objects as individual objects. We can't analyze it as a system. Because if I analyze it as a system, that tension is what we call internal. I can't find this inside because I've already analyzed the whole thing. So what we need to do is we need to analyze each object separately. Now, when we analyze each object separately, that means each object needs its own free body diagram. And then you have to write the forces that are acting on each object. And so we're going to do that here. We're going to come down here and we're going to analyze each separate object. And so if I look at object B, I'll start with object B. It has, of course, a normal force, but just of it, right? So it's normal force of B. It's got its own weight. It's got nothing, because we said no friction, nothing's trying to pull it back. But look what's pushing it forward, or pulling it forward. The only thing pulling it forward is the tension on that string between the two blocks. And then if I look at so this is object B. So let's make that known. This is free body diagram of B. And then if we do the free body diagram of A, we can see that it has its own normal force. Of course, it has its own gravitation, its own weight. And then that tension, which we had mentioned before, trying to pull B forward, is the same tension that is trying to hold A back. And of course, the original force is what's pulling on A. Now note, that force here, that's only pulling on A, right? That's directly connected to A. So we can't connect that to B. Now, it's daisy chained together, obviously, that if we use, the force to pull A forward, that creates the tension in the string, and that tension is what pulls B forward. So there's a daisy chain effect here, but the 10 newtons does not act directly on B. And then once we do this, we can set up equations for each free body diagram. And once we do that, then it becomes kind of a math game. We don't want to forget the physics that's happening here, but summation of the forces in the x direction equal ma. And in this particular case, for object B, the only force acting is force tension. And that equals MBA. And right now I can solve for tension. I can solve it right now. I had already done the analysis for the whole system. I knew the acceleration is 3.33. I can go and do this right now. Force tension equals 2.0 kilograms times the acceleration of 333 of the system. Because remember, that acceleration is going to be the same for everything moving in that system. And then you can find that force tension. Force tension equals 6.67 newtons. And again, that 3.33 was repeating. So if I go and double, it's going to be 6.67 eventually, if I round it correctly. Now, what I can also do with this, although I don't really need to do it right now for object B, is I can do summation of forces in the y equals 0. We know that F, the normal force, minus the force of gravity, are going to equal 0. A little sloppy, sorry about that. This just is going to tell us that the normal force is equal to the gravity. We don't really need to do that for this particular problem. There's no need to. I mean, we had already solved it, but I just wanted to show you that. You can do the same thing for A, right? For the A direction, for the A object, you can just replace these B's with A's, and same thing in the Y direction. The normal force of A and the gravitation of A, they're going to be equal but opposite, because there's nothing pulling at an angle causing the normal force to change. But that's going to be important if and when there's friction, so we'll just keep that in mind. Get rid of it for now. I do want to show you, even though we don't need to, I do want to show you summation of the forces in the x direction for object A. Because for this particular example, we do have the force, that's positive, minus the force tension, right? Equals MA. Actually, I should back up here. This is M mass A times acceleration. And I can plug in what I know. I know 10.0. And let's pretend we didn't solve for friction before, or for tension before. Let's pretend we're still solving for it. And we know the mass, 1.0. And we know the acceleration, 3.33. And then if you solve this algebra, well, the force of tension is still going to be 6.67 newtons if you solve that. Which, it better match. It's the same exact tension, just equal but opposite direction. Okay? So, that is solving it without any particular friction. Now, there is another way to solve this without actually doing the whole system first. If you keep it as just two objects, oopsie. I'm going to call this method 2. If you do this, if you never go and solve it as an entire system, if we had never done that part, you can still solve these problems if you look at these individual, if you look at just these two formulas. Okay, if we repeat those two formulas, I'm going to rewrite them. Okay, but we're going to pretend we never solve for acceleration. Okay, so keep that in mind. We never solve for acceleration. So, we need to define the free body diagrams of each individual object. We need to do that very clearly. And what we are going to discover here is, we're pretending we never solve for acceleration. So in this problem, we're looking for force tension, and acceleration. So we don't know those things. But we do know the mass and we do know the pulling force. So if you look, we have two unknowns and two equations. Well, if you have two unknowns and two equations, you can solve, but you just might have to do a little bit algebra. You might have to do a little substitution. And there's a bunch of different ways you can do that. But if I'm trying to find acceleration, there's a bunch of different ways you can attack substituting or setting equations equal to each other. What I'm going to do is I'm going to rearrange this. Solve for A. And then I'm going to take that and I'm going to plug it in over here. And I'm going to say, well, F minus Ft equals ma, and then I'm going to plug in the Ft over mb for the acceleration. And then, you know, that gets a little funky, so let's start substituting in what we know. We know this is 10.0. We know we're looking for the force tension. That's what I'm solving for, because I kind of pretended I didn't find that acceleration before. I know the masses. The masses are 1 over 2. So I'm going to do a little algebraic rearrangement right here. I can take that MB and put it under the MA there, right? And I'm going to have FT here. And then what you'll end up getting if you solve this or rearrange it is 10.0 equals 1.5 Ft. And then if you divide that, you're going to get a force tension of 6.67 newtons. Huh, yeah, of course it is the same, so it should be the same. And then of course, once you get that 6.67 newtons, since we did not solve for the acceleration before, we pretended not to solve for the acceleration before, but we can take that answer and plug it into the previous equation, and then we can solve acceleration. We can say, okay, well, 6.67 divided by 2.0 equals acceleration. 3.33 equals meters per second squared equals acceleration. And so you can solve these problems and never have done solving it as one full, complete system. Right? You can do it without doing the overall calculation. You can do it by ignoring that and completely doing it as two independent objects with two sets of equations. You just might have to do a little algebra and do a substitution. And this method, believe it or not, is going to come up more often than not. So be aware of that. Okay? All right. So check that out. Now, I'm going to, in the next video, I'm going to introduce friction.